Section 1.2 is a little bit longer compared to our first section, okay? And we've got some key terms that we need to pull out of this section, okay? But as we go through it, I'm hoping you'll see that a lot of this material is familiar. And Section 1.2 is all about phases and classification of matter. Matter we alluded to in the first video, right? Anything that occupies space and has mass, right? When you take the mass of something, you're measuring how much matter it has. And you've, of course, heard of these at some point. Three most common states or phases of matter: solids, liquids, and gases, which are defined by the shape they take and whether or not they take the volume of the container, okay? So solids are rigid, have a definite shape, right? Liquids flow. They take the shape of their container, but not the volume. The gas takes the shape and the volume of its container, right? And the difference there is whether or not it spreads out throughout the entire thing. Okay, so a cup of water settles down to the bottom, takes the shape, but not the entire cup. Okay, whereas a gas expands the whole way, takes up the whole volume. Okay, so solid, liquid, and gas. We'll be working with those this semester. Yes, there is a fourth state of matter, plasma, right, which does have its usefulness, like plasma torches and things like that, right? What is it? Gaseous state of matter with electrically charged particles within. And those electrically charged particles, be it positive or negative, give it distinct properties compared to other gases. Okay, not something you're going to find in your bedroom or the classroom, found in high temperature environments, stars, lightning. We do have it. I just mentioned man-made applications, plasma torches, plasma TVs are outdated at this point. They've been replaced by LCD and LED. Certain analytical instruments in chemistry use plasma. Okay, but again, nothing we'll talk about in depth this semester. But we did introduce the idea of mass. Let's think about what mass is compared to weight. I've already said the first point there. Mass is the measurement of the amount of matter. Okay, so that's a constant value no matter where you are. Whereas weight, right, is the force that gravity exerts on an object. So it's proportional to the mass, but it's not equal to, because as the force of gravity changes, the weight changes. Okay, so the easiest diet plan is just to go to the top of Mount Everest or the moon. Less gravitational pull, lower weight. Okay, so an object's mass is constant no matter where you are. It's something that you measure with a balance, okay, proportional to a standard. Weight will change depending on where you are because it's based on the force of gravity. And that brings us our first law, okay? The law of conservation of matter. And this is something you do have to know. Law of conservation of matter. No detectable change in the total quantity of matter present when matter converts from one type to another. So when a reaction happens, you start with things that are called reactants. You produce things that are called products, okay? But the mass that you start and finish with is the same, no matter if you're going through a chemical change or a physical change. We'll talk about the differences between those shortly. Okay? So if we take an example like brewing beer or a car battery, right? These things work. If you bottle up beer, eventually it produces alcohol. Maybe you've done home brewing, okay? Or you're familiar with a brewery tour, right? You cap the bottle, the mass doesn't change, but a chemical reaction happens to produce ethanol. That's the alcohol that would get you drunk. A battery works, right? Produces electricity, but it has a law of conservation of mass. It does not change. Law of conservation of matter, law of conservation of mass. You can use those two interchangeably, okay? Because mass is a measurement of matter. So the next question is, what does this matter actually consist of? Well, we've got different types of matters. We've got atoms, we've got molecules, okay? And these are the things we're going to have to start to pay attention to. You're probably good with solid, liquid, gas, but make sure you know the difference between an atom and a molecule, for example. What is an atom, right? Well, if you visualize just taking something and cutting it in half and half and half and half and half and half until you can't anymore, right? That is where you would reach the atom, the smallest particle of an element that has the properties of that element and can enter into a chemical combination. And the key word there, the key phrase, is that it has the properties of the element, because you probably know that there are things smaller than atoms, protons, neutrons, things like that, okay? But it maintains the properties of that element, an atom does. Okay? And then a molecule is at least two atoms. Could be the same atom, could be different atoms. Two atoms connected by a strong force, that's called a chemical bond. And here we see gold atoms, right, that we can approximately visualize using technology that's using STM, but I've already mentioned the fact, right, we can't actually zoom in and see individual atoms or molecules. Don't have the technology yet. These things are small and light. You can probably get an idea for that, right? Carbon atom diameter, look how small that is and how light it is, right? Taking lead atoms, 300 trillion of them, still negligible. If you're trying to visualize it in the world around you, you've probably had one of those days where you've accidentally walked into a spider web. If you visualize just a single string of a spider web, right, that's 7,000 carbon atoms across. And it's hard to get individual atoms, even in chemical reactions, right? Most are found in molecules or in compounds, right? It would only be noble gases, the group 18 on the periodic table, that we could easily get individual atoms of. And it wouldn't even be easy. I shouldn't put it lightly. Okay, so molecules, we talked about this already, right? Just a couple things are individual atoms, lots of things are molecules. Here we see hydrogen, oxygen, phosphorus, and sulfur. These things move as a unit. Okay? So you'll never find them existing just on their own. It's always 2 hydrogens or oxygens paired together, 4 phosphorus, 8 sulfur, and they move as a discrete unit. Okay? Think about it like keys on a ring. They always move together. Or a 6-pack, right, of soda. It's always traveling together. And here we see some other examples of molecules, now with different things that are connected: hydrogen and oxygen, carbon, hydrogen, and oxygen, and glucose. Okay? So we know atoms and molecules, but we need to know how to classify things a little bit further, and this might be the challenging part if you're okay with atoms and molecules. Make sure you also know the difference between a pure substance and a mixture. This is how we'll finish section 1.2. A pure substance is something that has a constant composition throughout. So it is 100% the same throughout the entire thing. So an element is something that's an example of a pure substance. And an element is a type of pure substance that can't be broken down any further by a chemical change. It's just one element, okay? So it could be something like gold, where there's just one of them. Could be phosphorus. We just saw that has 4 atoms in a molecule, or oxygen, 2 atoms in a molecule, but it's just one element. So elements can be atoms or molecules, but they're pure, and we can't do any sort of chemical change to simplify them further. Okay. Hopefully that makes sense. Right? And that gives us the periodic table of the elements. Right? Some of them are found naturally, some have been created in the lab, but you're familiar with this idea of the periodic table, and it's synonymous with chemistry because we use it all the time. Anything that's on the periodic table is an element, and it can't be broken down any further. Okay, so there's also compounds. Compounds are still pure substances, but the difference is they can be broken down into something simpler by doing a chemical change, because we've got at least 2 types of things that are connected. Okay? Notice in all of those examples of compounds, there's 2 different atoms in there. So we can do some sort of chemical change to simplify them further. They're pure throughout, so they're a pure substance, but these compounds can be simplified further. Okay? And that's what makes them different. And while we only have a little over 100 elements, there are millions and millions of compounds, right? There's 14 million organic compounds that are currently classified, a ton of them. Okay? And different changes can simplify these things. Could be as simple as heat or light, a process in chemistry known as recrystallization, right? So here we see mercury 2 oxide, right? If you heat it, you can break it down into mercury and oxygen. So mercury 2 oxide, that's a compound. Okay? Mercury and oxygen are elements. So you take a compound, you heat it, and you simplify it into elements. Both compounds and elements are pure substances. Okay? And that's summarized on this slide here, okay? 35. Good summary slide. Atoms and molecules, elements and compounds. Know what they mean. Because an atom, there's always just one of them, so it has to be an element. And a compound, we just said, has to have two different things. So it's always a molecule or an ionic compound if they're ions. Okay, but in the middle is where it gets tricky, because a molecule could be an element if everything in there is the same, like H2 or S8. Or it could be a compound if they're different. An element might just be one atom, okay? Or an element can also be a molecule if everything's the same, like O2. And this slide in the middle here, number 36, this is a really nice way to help you review atoms and molecules, elements and compounds. But what about if it's not a pure substance, right? Pure substances, elements and compounds, those are pure substances. But if it's not pure, then it's known as a mixture, okay? And a mixture is composed of two or more types of matter that can be separated by a physical change. Notice the difference there. Now we're separating it by a physical change, not a chemical change. So doing something like evaporation, that's a physical change. And there are two types of mixtures, homogeneous mixtures and heterogeneous mixtures, and you need to know what those mean. Know those terms, homogeneous mixture and heterogeneous mixture. What are their definitions? Okay. A homogeneous mixture, uniform composition. It is the same throughout. Okay. They're sometimes called solutions. So something like Gatorade, okay, the first sip and the last sip, they're the same. Gasoline, fill up your tank. The beginning of the tank and the end of the tank is the same. Heterogeneous, composition that varies from point to point. Okay? Sand on a beach, for example, you might have a bunch of shells in one area. You might have some litter in another area, right? It will vary from point to point. Dressing, Greek dressing on a table, right? The heterogeneous mixture, especially when it separates out oil and water. A chocolate chip cookie could be a heterogeneous mixture, right? You could have one bite that has a bunch of chocolate chips and then another worse bite that barely has any. So know the difference between those. Mixtures are not pure substances, and there are two types, homogeneous and heterogeneous. We can separate them out by physical changes. Okay. Here's the two different types I talked about. And we finish with slide 40 here. This is a big, big part of chapter 1, especially if you've forgotten these things from when you first took chemistry. Know atoms and molecules, elements, compounds, and then the two types of mixtures, homogeneous and heterogeneous. And a lot of that information is summarized nicely here. So that wraps up section 1.2. Okay. Big part of chapter 1. Make sure you know what all those different things mean. They'll definitely show up on the test. Okay. And then we'll elaborate on that a little bit further, those chemical and physical changes and properties in section 1.3.